Hi, we're looking at the derivative of reciprocal trig functions. So reciprocal just means not inverse, but upside down of the original. So we know, for instance, that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. So cosecant is the reciprocal of sine, and the way to remember it is look at the third letter. The third letter of cosecant is S, so it means sine, and in future they're going to abbreviate that to CSC. Secant is the reciprocal of cosine. Again, the third letter is C, so it matches with cos. And cotangent, third letter is T, so it matches with tan. So cosecant is often just CSC, sec. So this is sec, cot. This is cosec, sec, and cot is what they're normally shortened to. Okay, so the third letter is S, so we just flip up the relationship. So instead of opposite over hypotenuse, it's hypotenuse over opposite, etc., etc. Okay, so they're the definition of the reciprocal, not inverse reciprocals. Okay, just to prove that they have a graph. Okay, so what I've done in the first one. Okay, so then you can see sine is there. Okay, so when you flip 1 upside down, you get 1. When you flip minus 1 upside down, you get minus 1. But as in the sine function, as sine gets smaller, when you flip it, it gets larger. So when sine gets smaller, when you flip it, you get larger. This is negative, so it goes down. So that's what the graph looks like in this unit 12 spec methods. We're not actually drawing the graph, but I'm just showing that it does have a graph. And if it does have a graph, it does have derivatives. It does have gradients of tangents. Okay, so that's what cosecant looks like, the inverse of sine. So here's cos. Okay, so cos is just there, etc. Okay, so there's 1. So when you flip 1, you get 1. So as cos gets smaller, secant gets larger. When you flip minus 1, you get minus 1. And as cos gets smaller, secant gets larger. So it's the same shape as the cosecant, but it's just like a phase shift across. Okay, and again, we've got gradients of tangents. Okay, again, in this unit with 12 spec methods, we're not drawing it, but I'm just showing you that it does have a graph. And the tangent graph, so here's tan. This is what tan looks like, and it just repeats. Okay, so here's 1, so when you flip 1, you get 1. So as tan gets larger, cotangent gets smaller, and it asymptotes there. So when you flip, so as tan gets large, we're going to get smaller and smaller, and then we'll turn over. So the blue line is the cotangents. Okay, again, we're not drawing the graphs, we're just showing that there has a graph. Okay, so now we're going to look at the derivatives. Okay, so these are the answers. Okay, so just copy that into your notes, and on the next page we're going to prove why. So sec turns into sectan, cosec turns into minus cosec cot, and cot turns into minus cosec squared. Now I don't learn these off by heart. You can just do in a test situation, you can do the proofs pretty quickly, and I'll show you what they look like. But if you're going to put them into your notes, please do so. Okay, come across when you're ready. Okay, so by definition, sec is 1 over cos, and so we've got a quotient, so u equals 1, so u dash equals 0, v equals cos x, so v dash equals minus sin x. And so we're doing v u dash minus u v dash over v squared. Now that equals 0. Okay, so we've got minus times the minus the plus, so we've got sin x over cos squared x. Sin x over cos x equals tan x. So one of those coses and that sine join together to get tan x, but you've still got one cos on the bottom because you only use 1 to get rid of that one, and 1 over cos is the same as sec. So that's the proof, the first proof, but there's another proof that I'll just now show you now. So sec x is 1 over cos x, which is cos x to the minus 1. Okay, so the derivative of sec x is using the chain rule, so multiply by the power, don't change the bracket, subtract 1 from the power, and then multiply by the derivative of the bracket, which is minus sine x. So minus times a minus is a plus, so we get sine x over cos x squared, which is what we've got there, and then finish off the proof to get that one. Okay, so we'll do the next proof next. Okay, so we've got cosec there, so third way to sine, so it's flip. So u equals 1, so u dash equals 0, v equals sine x, so v dash equals cos x. So we've got v u dash minus u v dash over v squared, so that's 0. Minus 1 times cos x is minus cos x. So we've got cos x over sine x, which is going to be cot x, but it'll be a minus. So there's my minus cot x. But I've still got one sine left, and 1 over sine is cosec. Okay, so that's the first proof, how it works. And similarly, cosec x equals sine x to the minus 1. So the derivative of cosec x equals multiply by the power, don't touch the bracket, subtract 1 from the power, multiply by the derivative of the bracket, which is cos. So I get minus cos x over sine x squared, which is the same as that, so it finishes off the same. Again, I don't know these off by heart, I can just do a proof of them quickly if you need to. And the last one, so I've got u equals cos x, so u dash equals minus sine x, v equals sine x, so v dash equals cos x. So I've got v u dash minus u v dash over v squared. So minus sine squared is the first one, so there's a minus there, minus cos squared over sine squared. And so minus is common to both, so I take the minus out, and then sine squared plus cos squared equals 1, which is a fundamental theorem. So I end up with minus 1 over sine squared x, and sine is cosec, so it's minus cosec squared. Okay, so that's the last of the proofs. Okay, so that's it. So obviously with these ones we can use, so for instance, if you've got cots, if y equals cot 2x minus 1, then derivative, so cot turns into minus cosec squared, 2x minus 1, and then multiply by with the chain rule, multiply by the derivative of the bracket, which is 2, so end up with minus 2 cosec squared, 2x minus 1. So you can still use the chain rule in complicated functions. Okay, that's it. Bye.